We've done a lot of probability things, and I think that's neat. It's something that you need to know. I want to spend a little time today talking about some algebra ideas. We do a lot of things in algebra that, a kid will look at that and think, well, why do I need, I'm never going to be put in this situation. I never have to fool with this. And I'd like to show you today kind of a nice little thing that you could do that involves algebra, and you have to know how to do some things. The first thing I want to talk to you about is how to find polynomials through a point, through a series of points. And we're going to use this to model real-life situations. One of my little pet peeves, flash up this word problem that I found in an algebra book. Here's a drug administered orally. The concentration in the blood rises sharply to a maximum, modeled by the function. And they give you this horrible degree 4 polynomial. And then say, okay, what's the maximum level of medicine in the patient? When does it occur? And that's good stuff. You can then graph this curve, and you can use your calculator, or later on you can use calculus to find the maximums of it. But the thing that bothers me about this is this curve they gave you. When on earth are you ever going to be given a problem where they give you this formula? I mean, that's unrealistic to think, they just pop out of the air. There's a way to get these, but they never discuss where they come from. And that's what I want to do today, is show you where that formula comes from, or how you can kind of generate that formula given some data. And that's going to require us to know this little trick for finding a polynomial of degree n or less through n points. What you want to do is, for each point that you have, you want to create a polynomial that's 1 at that point's x value, but 0 at all the other point x values. It's called Lagrange polynomials, after Joseph Louis Lagrange. He's a French mathematician, actually born in Italy, so Italy kind of claims him as well. And then once you have these things, we'll take the right amount of each one of them, and the right amount is just whatever that y coordinate is for the point, so that we go through each of the points, and then we expand the polynomial, multiply, collect like terms, and so forth, and that gives us the answer. So let's start off easy with 2 points, and I'll show you how this works. I'd like to build something that is 1 here and 0 there. So what I do is I'm going to include an x minus 4. That way when I plug in 4, that will be 0. And then as far as making it 1, well, let me plug in 0 and then solve for c. And so I just divide by the junk. I know that's a negative 4, but I'm leaving it there because I want to show you the pattern. Okay? So the first one is x minus 4 over 0 minus 4, and you can kind of simplify that. The second one, you do the same thing. I want now x minus 0, and then the bottom will be 4 minus 0. So I've kind of swapped out things, and that simplifies. And then to get these things through the point, I want 3 of the first one and 8 of the second one. And so you can kind of multiply that out. 3 times this would give me 3 minus 3/4 x, and then 8 times that would give me 2x. Simplify that a bit more. You've got 5/4 x plus 3, and when you graph that, you'll see that that does go right between those 2 points. Now that is a hard way to find the line through 2 points. The easier way to do that, is to find the slope of the line through the points and then use the point-slope form of the equation. But this generalizes. The other won't. Let me kind of bump up the odds here and go to 3 points and show you how that looks. If I go to 3 points, now I want something for the first one that is 0 at 3 and 4. So I throw in an x minus 3 and an x minus 4. And again, I want it to be 1 when x is 0. So I plug in a 0, set it equal to 1, solve for c, and you just divide by the junk. Okay? So you see the pattern here. I've got my 3, I've got my 4, that's the other x values. I've got the x's here, and then I've got the x value for the first point down here. If I follow that pattern, I keep doing that. Here's for the second one, the 0 and the 4, and then I plug in the 3. For the third one, I put in the 0 and the 3, and I plug in the 4. It's a nice little pattern to follow, and then you can multiply all that mess out. I want 3 of the first one, that's the y value here, 6 of the second one, and 8 of the third one. You do all that arithmetic, you do all the algebra necessary to clean that up, and you get this little formula It's a quadratic, it's a degree 2 polynomial, and when you plot that, you'll see that it goes right through those 3 points, 0, 3, 3, 6, and 4, 8. In fact, it's even nicer than that because if those 3 points had been collinear, it would have gone ahead and given me the line through those 3 points. So now to prove that is a different deal, but it actually gives you the lowest degree polynomial that will go through those points. So it's a neat little trick. Lagrange polynomials, I don't know why we don't teach that, to be honest with you, because you're not doing any calculus. You're just doing some basic algebra. That's what you're doing, kind of multiplying things together. It's got a beautiful little pattern to it. I think it's really cool. So let me give you a situation. This is something that you could do. You could try this out yourself. Suppose you're modeling your trip from Glasgow to Bowling Green, and on one hand you're timing yourself. You've got a watch timing yourself, and then you've got your trip odometer set to measure the miles. So you leave Glasgow, you start at 0 in time, 0 in miles. And then when you get on the Cumberland Parkway, 5 minutes later, you've traveled 2.5 miles. When you eventually get to I-65, you've traveled 17. You've been traveling now for 17 minutes, and you've traveled 15.5 miles. 32 minutes after you start, you get to exit 26, get off the I-65, you travel 31.7. And then you reach your destination in 42 minutes. Your trip odometer says 35.9 miles. So the question would be, can I find a nice, smooth kind of curve through those points that I could then use to do all this other stuff we talked about, find the maximum, and I'll show you some other stuff you can do with it. Well, if you take these points, and all I've done is just kind of collect the data and put them into points, you do this little stunt we talked about, where you generate the Lagrange polynomials for each of the 5, okay? And I know it's messy, but you can see the pattern. 5, 17, 32, 42, and then down here you divide by putting in the 0, the 0, the 0. You do that each of the times, okay? Here are your points. I've plotted minutes versus miles traveled, okay? You do all that arithmetic, and then you want to add 0 of the first polynomial, 2.5 of the second, 15.5 of the third, 31.7 of the fourth, 35.9 of the fifth. I grant you it's messy, but it's just doable stuff. You can do this. And that gives you this formula, which if you now plot that, it's messy looking, but if you plot that, you'll see that it goes right through those points. Easy as pie. I think it's really kind of cool. And then once you have this, you can extrapolate information. You don't just have to do things at data points you collected. You can then look at, well, what was my, for example, average speed? I'm going to talk to you in just a second about how you calculate average speed. You can calculate things like that between the points. That's a nice little trick, and I know I did it kind of fast, so I'm going to flash up a page that has that formula on that, give you a chance to copy it down, and then always you can go to the web page if you need to and get it later.